Increasing rotational speed and reducing radius can improve energy density and reduce friction loss. Previously, several videos explained the principle of converting thermal energy to electrical energy using centrifugal force and gravity. These videos also envisioned how this principle could help humanity in long-duration space travel. Now, let's take some time to answer questions raised by readers. The main concerns are: 1. The converted energy is too small. 2. Air resistance is too high, making power generation inefficient. To address these issues, I have at least 4 solutions. Due to space limitations, I will first explain the 2 methods, increasing rotational speed and reducing radius. The other solutions will be discussed in future articles. 1. Increasing rotational speed. The size of centrifugal force directly affects the generated voltage. Thus, the first method is to increase rotational speed to enhance power output. According to basic physics principles, centrifugal force is proportional to the square of angular velocity multiplied by the radius, as shown in equation 1. F sub n is proportional to omega squared r. Here, lowercase r represents the radius, and omega represents the angular velocity. The generated electric field is proportional to the centrifugal force, which means the field strength is proportional to the square of the angular velocity. Under the same generator size, assuming the total resistance is constant, the output power can be obtained as the square of the voltage divided by the resistance, based on basic electrical equations. Referring to equation 1, the output power can be derived as proportional to the 4th power of angular velocity, as shown in equation 2. P sub Lec equals V squared divided by R is proportional to F sub sin squared divided by R is proportional to omega to the power of 4 R squared divided by R. Here, P is power, capital V is voltage difference, and capital R is resistance. The frictional loss of the rotating body is approximately proportional to the square of its velocity, as shown in equation 3. P sub friction is proportional to V squared equals open parenthesis omega R close parenthesis squared equals omega squared R squared. Here, lowercase v is the velocity, which is approximately proportional to the square of angular velocity multiplied by the square of the radius. Comparing equations 2 and 3, equation 2 represents the generated energy, which is positive, while equation 3 represents energy loss, which is negative. Combining these equations yields the approximate net energy equation, shown as equation 4. P sub net equals P sub Lec minus P sub friction equals A omega to the power of 4 R squared minus B omega squared R squared equals open parenthesis A omega squared minus B close parenthesis open parenthesis omega R close parenthesis squared. Here, A and B are system constants, both greater than 0. From equation 4, it is evident that there must exist an angular velocity where net energy output is greater than 0, as long as the rotational speed is sufficiently high. Thus, we see the effect of the first method, increasing rotational speed. At this point, the second issue arises. When the rotational speed becomes too high, the centrifugal force exceeds the yield strength of the supporting structure, causing the structure to collapse. This is where the second method comes into play. 2. Reducing the radius. By substituting equation 1 into equation 4, the net energy can be expressed using equation 5. P sub net equals A omega to the power of 4 R squared minus E omega squared R squared equals CF sub sin squared minus DF sub sin R. Here, C and D represent different system constants, both greater than 0. From equation 5, it can be seen that under the same centrifugal force, that is, at the structural force limit, the radius term is negative. This means that the smaller the radius, the greater the net output power. To make this easier to understand, we can look at the diagram above. The mass of the object on the left is the same as that on the right, but the rotation radius on the left is larger, while the rotation radius on the right is smaller. Rewriting equation 1 as equation 6, we can derive the relationship between velocity and radius under the same centrifugal force. F sub sin is proportional to V squared divided by R n. F sub sin 1 equals F sub sin 2 implies open parenthesis V1 squared close parenthesis divided by R1 equals open parenthesis V2 squared close parenthesis divided by R2. From equation 6, we can see that when the centrifugal force is the same, the speed of the larger radius must also be greater, while the speed of the smaller radius can be lower. Because the energy loss caused by air resistance is approximately proportional to the square of the velocity, the energy loss for the larger radius is also greater. For the smaller radius, the energy loss due to resistance is smaller. This corresponds to the d term in equation 5, which increases with the radius, reducing power output. Therefore, under the same centrifugal force density, composition, and volume, a smaller radius results in greater net energy output. Another noteworthy point is that, as shown in the diagram, the same centrifugal force requires the same structural strength, e.g., the rope in the figure. However, the total length of the structure required for a larger radius must also be greater. Thus, under the same centrifugal force density, composition, and volume, smaller radii require less structural material. In other words, reducing the rotation radius simultaneously decreases resistance and reduces the amount of structural material needed. The previous two methods significantly enhance the feasibility of implementing a thermoelectric system. Consider the energy systems for space travelers mentioned in earlier videos. As shown in the figure, the blue represents the spaceship's outer shell, the brown represents the inner shell, and the purple represents the thermoelectric generator. The left side shows a system with fewer but larger generators, while the right side has a system with more but smaller generators. Based on the derived results, it is evident that the smaller and more numerous generator systems on the right have a greater advantage. This configuration is more likely than the fewer, larger generator systems on the left. Of course, it can be made even smaller. Thus, increasing the rotational speed and reducing the radius can resolve most of the issues.